Welcome everyone, and this is Rajasekar, and I will be taking a seminar on case hardening and hot freezing techniques. Before entering into the topic, you must all know that what is surface hardening. It is nothing but enhancing the hardness over the surface of the components. It is just a selective hardening, and it is done to withstand the fatigue and impact loads. It is to be done necessarily in the components like transmission shafts, gears, etc. As a result, you will get a hard outer surface and tough inner core. Then the difference between the surface hardening and the conventional hardening technique. As I said before, the surface hardening is a selective hardening of the material. Here it is the hardening of the entire material, and here soaking is not required. Soaking is nothing but maintaining at a particular temperature in order to get uniform distribution of temperature. Um, and here, as it is a selective hardening process, don't need soaking. But here, soaking is to be done in order to distribute the temperature uniformly. Only then you will get a uniform hardness, and there is a variation in hardness between the core and the outer surface of the component. Here, it is a uniform hardness from the core to the outer surfaces. Then the classification of surface hardening technique. It is broadly classified into case hardening and quench hardening. Case hardening is further classified into carburizing, nitriding, cyaniding, boronizing, chamferizing. And here, quench hardening is further classified into induction hardening and flame hardening. In this, we'll be seeing the case hardening and its subtypes. First of all, case hardening. It is one of the types of surface hardening process, and it involves packing the low carbon ion within a substance high in carbon, thereby increasing the hardness of the outer surface. Then the system is heated to enhance the migration of the carbon into the component surface. It is a process how it is to be done. Thereby, then the hard layer will be formed, as we all know that the thickness decreases from the outer surface to the inner core. And its application and types. It is often employed for low carbon and medium carbon steels. Since high carbon steels are directly bench hardened, here only the low carbon and medium carbon steels are uh, employed under these case hardening techniques. And if needed, we can employ both the tool and alloy steels. And as I said, the flame hardening and induction hardening will not hold good for the above steels, as due to the lack of carbon network. Just tempering and quenching will not give you any favorable results. Hence, we are employing these case hardening technique. It is usually to overcome India and to withstand various loads that I mentioned before. It is classified into carburizing, nitriding, cyaniding, boronizing, chamferizing. Let's see one by one. Then this is the process flow. Let us first identify the suitable process parameters, which is followed by application of various heat treatment strategies. Then, depending upon that, we'll be going for various types of case hardening. Then, uh, once the case hardening is completed, we'll go for the hardness test. Carburizing technique is the first type of case hardening. It is a thermochemical process in which the carbon is diffused into the outer surface of the low carbon steel or medium carbon steel, uh, increasing the carbon content to sufficient levels so that it will respond to the various heat treatment process. Like then it will be tempered and quenched to obtain the martensite structure. Then it produces hot wear resistant layer. The most important point is that the thickness of the layer depends on the time of the process. That is, the time taken for carrying out this carburizing process means a lot. The time taken is given by thickness divided by 0.2 plus 3. It holds good for all the four types of carburizing process that mentioned below: the solid or packed carburizing, liquid carburizing, gas carburizing, and vacuum carburizing. Then first, solid carburizing. In solid carburizing, the source for the carbon that is charcoal, barium carbonate, or leather scraps, bone char, etc. And the temperature is usually maintained between 850 degrees centigrade to 950 degrees centigrade. Then comes the process. It is usually carried out inside a airtight chamber, and the components are sandwiched. That is, the component is to be solid carburized, which is sandwiched between the carbon-rich materials. When it is placed inside the furnace, the atomic carbon is released. Due to the high temperature, the carbon will be atomized and it forms a carbon layer around the surface of the component. Then the thickness of the carbon layer will be raised to 1.5 mm after maintaining in the furnace for about 10 hours. Then it is followed by generally quenching uh, using a water or any other quenching agent to obtain the required bubbles. Then advantages and disadvantages of solid carburizing. First of all, advantages, we get a good combination of hot surface and tough core. That is what we needed actually. Then good adherence by diffusion. Then the disadvantages is that dimensional diffusion takes place. We couldn't control the thickness of the carbon layer here, and the process comparatively slow. As we said, uh, for 1.5 mm thickness, we need to carry out the process for about 10 hours, and the surface finish is poor. As I said before, the controlling of the controlling the thickness of the hard layer to be formed is a tedious, a difficult process. This is nothing but the container within which we'll be doing the solid carburizing process. Then liquid carburizing. Here the source is nothing but a salt bath containing 80% of sodium carbonate and 10% of sodium chloride along with the 10% of silicon carbide, and the temperature is maintained between usually around 850 degrees centigrade to 950 degrees centigrade. Then the process, the component to be liquid carburized is placed inside a salt bath. Then the temperature of the bath is raised to release the to get that atomized carbon, which diffuses into the surface of the component to be liquid carburized. The thickness of the layer is increased by zero point 0.5 mm to zero point 0.6 mm after maintaining it for about 1 hour. Then it is followed by the similar to that in solid carburizing. It is followed by a conventional quenching process to obtain the molten sodium structure. That is hot structure. Then advantages and disadvantages of carburizing. The advantage is that the proper composition of salt bath provides uniform depth of the carbon layer and the freedom from oxidation and soot problem because we are not exposing to the environment. Hence, the oxidation problem will be controlled. Then the disadvantage is that controlling the thickness of the garment, that is the preparing the proper composition itself a difficult task. Then the process slower than uh, it is faster than solid carburizing, but a little bit slower than the gas carburizing process. And the below picture shows that a component taking out from a molten bath, that is the salt bath. The next comes the gas carburizing. The source is nothing but the gas with high carbon content, such as methane, ethane, propane, etc. The temperature is maintained between 850 degrees centigrade and 950 degrees centigrade. In the process, that is the workpiece is held at high temperature in an airtight container. That the carbon-rich gas is passed over the component. As a result, the thin layer of carbon is formed over the surface of the component. Then it is followed by the conventional quenching process to achieve the hardness of the outer surface of the material. Then advantages and disadvantages of gas carburizing. The advantages is that the thickness of the carbon layer is controlled easily by controlling the passage of gases, and the surface finish is good. The time requirement is lesser in compared to both the solid and liquid carburizing process. And the disadvantages is that handling of hazardous gas is difficult, and gas generator is expensive. That is the initial cost requirement will be more in case of gas carburizing than the both solid and liquid. Then it's nothing but a typical gas carburizing process that I give below. Then the last type of carburizing process, that is vacuum carburizing process. The source is nothing but the gas with rich carbon content like methane or propane or ethane, anything. Then the temperature is maintained between 800 to 1100 degrees centigrade, and the pressure plays a major role. It differs from the gas carburizing in the area that it here the pressure plays a major role. It is usually carried out in a very low pressure, lower than the atmospheric pressure, that is 0.0012 to 0.027 bar. And the process, as I said before, it is a very low pressure near to vacuum, and the component is heated in the vacuum above the transformation temperature. Then the propane gas is passed The propane gas will break into carbon, hydrocarbon, and hydrogen. The carbon diffuses into the surface of the component and into the furnace. The remaining gases will be compressed. Then the advantages and disadvantages of vacuum carburizing. Advantages is that no intergranular oxidation takes place. As it is entirely carried out inside a vacuum container, that is very low pressure container, there won't be any intergranular oxidation, and the process is a bit safe. The disadvantages, that is initial cost requirement is big, because maintaining a vacuum is a tedious one, because it is not an easy task, right? Then formation of soot and tar takes place here, because we are not exposing anything out. It is entirely carried out inside the vacuum container. Hence, there is a formation of soot and tar. Also, obviously, it is there. Then the vacuum sample, it is shown below, within which the vacuum carburizing process is carried out. Then comes the nitriding process. It is a thermochemical. It is also a thermochemical process. It involves the diffusion of. It is a bit different from carburizing process. There the diffusion of carbon takes place. Here it is a diffusion of nitrogen into the surface of the component. It is usually employed on medium carbon steels and alloy steels. Usually, the presence of aluminum, chromium, and molybdenum on the surface of the component are usually preferred in order to, as we get an effective hot surface. Uh, then the ammonia dissociates and react with the above elements like aluminum, chromium, and molybdenum to form the hot layer. And the time taken will be around 20 to 80 hours. Then usually applied in the materials using guideways of lathe, which is an application. One of the applications I have given. Then then the source, the required nitrogen content that is obtained from the one and only ammonia gas. Then the temperature is usually maintained between 450 degrees centigrade to 550 degrees centigrade. That is, we can. It is obvious that it is lower than carburizing process. It is a kind of advantage, and let's go. Let's move on to the process. Uh, the one thing that before nitriding we should done is the decarburization. If it is not there, it will form a cyanide gas. It's highly poisonous. So before nitriding, decarburization is to be done. Should be done. Then the process carried out inside an airtight container as the above processes, and the container will be placed in the furnace in order to rise the temperature. Only then there will be a ammonia dissociation takes place. I give the equation for the dissociation of ammonia, dissociating to nitrogen and hydrogen. Uh, is when the time and the amount of ammonia increases, the thickness of the bond will increase. It is greatly depends on the time taken to carry out the process and the amount of ammonia we are supplying. Then comes the nine. Then complete the ammonia that we supplied, the entire ammonia that we supplied will not entirely will not be dissociated entirely. Only 60% of ammonia will be dissociated. The remaining 40% remain as it is. Then after dissociation, nitrogen reacts with the surface of the component and forms a molecule. Sometimes these atomic nitrogen produced will combine to form a molecular nitrogen and become stable, and it won't help in forming a hot layer. So the undissociated ammonia along with the hydrogen in the molecular nitrogen form will be flushed out. Then the basic advantage here is quenching is not required after the nitriding process. Then I have given some thickness for various time taken to carrying out the process. Then advantages and disadvantages of nitriding. The advantages is that the hotness will be more distortion and stress will not be induced. The dimensional changes will not be there. Then fatigue and wear resistance will be there. Then disadvantage is that the pre-processing of the component is required. That is mainly it denotes that the decarburization it is to be done uh, before nitriding process. Then then the next process is cyaniding. It involves the heating of iron-based alloy in contact with cyanide salt, that is cyanide-rich salt. As a result, the surface of the component absorbs both carbon and nitrogen and forms a very hot layer. Provides hot wear resistant surface with a tough core. And tempering will be done as in the every other above phases. Tempering will be done followed by quenching to obtain the required hardness. Then it is applicable for the small components like screws, clamps, bolts, piston pins, small gears, etc. Then it is further classified into three kinds, that is pack cyaniding, liquid cyaniding, and gas cyaniding. Let us see under one. Pack cyaniding. In pack cyaniding, the source is the mixture of charcoal and potassium ferrocyanide. Uh, it provides the necessary carbon and nitrogen content to form the hot layer, hot outer surface. Then the temperature is maintained at 550 degrees centigrade. Usually, the process carried out for 1.5 to 3 hours. In the process carried out inside an airtight container. At high temperature, the cyanide group is released. So it is to be held in a furnace, rise the temperature. Then the released cyanide groups react with the outer surface and produce. As the cyanide group contains both carbon and nitrogen, it forms both iron carbide and iron nitride, thereby increasing the hardness of the component ultimately. And it is often employed into the cutting property of tools, that is tool steels. Then comes the liquid cyaniding. In liquid cyaniding, the source is molten salt bath containing the mixture of sodium carbonate Na2CO3, sodium chloride NaCl, and sodium cyanide NaCl. Sometimes calcium cyanide CaCN2 is used instead of sodium cyanide. Then it is further classified into three types, that is low temperature liquid cyaniding, medium temperature liquid cyaniding, and high temperature liquid cyaniding. Let us discuss one by one. That first of all, uh, we move on to that low temperature. Here the temperature is maintained between 550 degrees centigrade to 600 degrees centigrade. The time taken will be around 5 to 30 minutes. The uh, will be achieved is around 0.02 to 0.04 mm of the hot layer. Then it is often practiced to improve the tool. Then medium temperature liquid cyaniding. Here the temperature is maintained between 800 degrees centigrade to 850 degrees centigrade, and the time taken varies from 5 minutes to 1.5 hours. It is quite long when compared with low temperature liquid cyaniding. The thickness varies from 0.075 to zero point 0.5 mm. Generally, it is applied to bolts nuts made of mild steels. Then comes the high temperature liquid cyaniding. Here, vary in the molten salt bath. There is a small change, a bit of change when compared with both about two methods. That instead of sodium carbonate, we'll be using barium chloride in the molten salt bath. Then the temperature is maintained between 900 to 950 degrees centigrade, as it is a high temperature liquid cyanidic process, and the time taken will be around 1.5 hours. The thickness varies from zero point 0.5 to 1.5 mm. It is a bit higher than the above two process. Then comes a gas cyaniding process. It is also called as carbonitriding. Then the source is nothing but the 30% of ammonia, a mixture containing 30% of ammonia and 70% of natural gas. The temperature is maintained between 850 degrees centigrade to 930 degrees centigrade, and the process is nothing but the process as follows: that gas mixture is passed over the component which is inside the airtight container, maintained in a furnace. And the atomic carbon is released from the natural gas, and atomic nitrogen is released from the ammonia. Since the amount of ammonia present in the mixture is comparatively lower than the natural gas, hence the percentage of deposition of carbon is relatively higher, because the source for carbon is higher, bit higher than nitrogen. Then it is a comparatively slower than the other cyanidic processes. Then the advantages and disadvantages of cyaniding. Cyaniding is a quick process, no distortion on the surface. Then high temperature, high degree of surface finish will be achieved. And disadvantage is nothing but, as we all know, cyanide gas is very poisonous in nature. Uh, then the process is expensive because it should be carried out with utmost care. Leakage of gases is hazardous to both. It's a threat to human health. Then liquid cyaniding. Uh, the the molten salt bath should be water free, because even a small percent of water leads to big explosion. So the main disadvantage is that it should be carried out with atmosphere. Then comes the boronizing process. Uh, it is also called as boriding. It is nothing but forming a borate layer not improve the hardness of the component surface. As we are boron carbides are used as a source of boron. Then that is boron carbides are rich in boron. From that we will be uh, obtaining our necessary carbon boron to form a hot layer. And the temperature will be usually maintained at 900 degrees centigrade. And the components containing iron, cobalt, nickel are often preferred because the boron has more affinity towards these materials containing these elements, hence these are usually preferred. Then hardness will be improved by the formation of iron borides, cobalt borides, and nickel borides. The thickness varies from 0.025 to 0.075 mm. There are two types of boronizing: solid and gas boronizing. Depending upon the purpose uh, and the limitations, we will be going for solid and we will be going for either of these two processes. And extreme hard and wear resistance can be achieved in boriding, also called as boronizing, and it is generally employed for tool and die steels. Then the last carburizing process, the last case hardening process, it is nothing but the champanizing process. It is similar to that of liquid cyaniding. The only difference is that there the source for nitrogen will be less. Hence, the carbon layer will be relatively a bit high than the nitrogen layer. Here, we'll be supplying additional ammonia in order to rise the nitrogen content in the outer surface of the component. The purpose is to generally, uh, besides the sodium carbonate, we add the ammonia gas. It is the main purpose is to increase the availability of nitrogen content, thereby improving the hardness of the outer surface of the component to be consumed. Then the last topic, hot phasing. With champanizing, we'll be disclosing the case hardening. The case hardening process here. Hot phasing involves the coating of harder material over the surface of the base metal, generally applied to make the base metal wear resistant in service. That is the ultimate aim of hot phasing. Then it will be applied to a new part, even applied to a new part, or you can apply to a worn out part to make it harder to withstand various loads. Then depending on the composition, they melt the hard material. The hard material we choose based on the depending on the base material. It should be there should be a compatibility check will be there in selecting a hard metal. Then the hard material will be melted in the range of 980 to 1200 degrees centigrade, and there are many types to done hot phasing, various welding methods. I mean, it is shielded metal arc welding, gas metal arc welding, plasma transferred arc welding, laser cladding, and thermal spraying, etc. I just mentioned some of the uh, general and process that we are doing often. There are many other processes to done hot fixing. Then thermal spraying, and spray fumes and welding process are generally used to apply the hot facing layer. Then commonly applied to materials include cobalt-based alloys, nickel-based alloys, and chromium carbide alloys. The most important alloy, that is the most important hot material used in spray fuse processes, nickel chromium boron silicon carbide alloy system, and SMAW, that is shielded metal arc welding and gas metal arc welding. Hot phasing process are effective in reducing the wear of the base material. Then, with these two processes, it is found that the lifespan of the base metal is increased approximately twice. Then it is followed by hot stamping to refinish the part to obtain the complete finished part. It is followed. The hot phasing will be followed by a hot stamping process. Then the advantages and disadvantages of hot phasing. The advantage is nothing but it extends the life of the components in service. This uh, we can hot phase a component uh, that is a newly produced applied to a newly produced one as well as the worn out one. Then it reduces the need for often replacement of parts. Then allows for the use of less expensive base material because i- there is no need of incurring more cost and base material as we are case or sorry hot facing with some other hard material. Then disadvantage is nothing but the relatively high cost as the hard material uh, will cost high and it is not the hot phase component cannot be used as it is. It should be hot stamped before usage. That is to get a finished part. So it is relatively high when compared to other not other process. It is uh, relatively high cost. Then two or more layers need to be formed to obtain the required hardness. It is two or more hard layers to be formed to obtain the required hardness. And the below diagram shows you a typical hot phasing process. Uh, that's it. Thank you. Um, thank you for giving me this opportunity. Thank you once again for your patience.